Welcome to qnawire.
Hi, so over here we're going to find what is going to be the crystal field stabilization energy for compounds going all the way from D1 to D9 on an octahedral field. So what is going to occur is that the Eg orbitals compared to the Tg orbitals are going to have an energy difference with respect to the very center of the energy, in which there would be no splitting and we would have all the orbitals at the same energy. This would be the energy for the actual compound, corresponding to minus 2 fifths of delta naught, and Eg orbitals are going to be higher in energy by a quantity equal to 3 fifths of delta naught. So for a D1 compound, the stabilization energy, the crystal field stabilization energy, would be equal to directly minus 2 fifths of delta naught. For D2, we're going to have twice this amount, so minus 4 fifths of delta naught. And for D3, we're going to have that the crystal field stabilization energy is going to be equal to 3 times this amount, so minus 6 fifths of delta naught. This comes from having one electron each on those orbitals. Now, what is going to occur is that for D4, the crystal field stabilization energy is going to depend on if we have a low spin or a high spin configuration. So I'm going to write down first the high spin case. This would be 3 times minus 2 over 5 delta naught plus 1 time 3 over 5 delta naught. Since in this case, for a high spin configuration, D4 would be the following arrangement: 1, 2, 3, 4. Okay, so in this case, the stabilization energy is going to be minus 6 fifths plus 3 fifths, would be minus 3 fifths of delta naught. Now, for the low spin case, the crystal field, or the low spin case, the crystal field stabilization energy would be equal to 4 times minus 2 fifths of delta naught. But in this case, we need to consider the pairing energy associated to the extra configuration. Remember that in this case, the splitting and the filling of electrons would be the following. So we need to add the contribution for the pairing energy required for this scenario. Some professors just omit this value, but in general, you should add it up to your calculations. So we would get minus 8 fifths of delta naught plus the pairing energy. Now let's go with D5. For the high spin case, this is going to be more simple. We're going to get that the configuration corresponds to one electron on each of the orbitals. So we will get 3 times minus 2 fifths of delta naught plus 2 times 3 fifths of delta naught. As you can see, this is going to give us a stabilization energy equal to 0. On the other side, for a low spin configuration, in the low spin case, the arrangement would be the following: 1, 2, 3, 4, 5 electrons. We would get 5 times minus 2 over 5 delta naught plus 2 times the pairing energy. So the crystal field stabilization energy in this case would be equal to minus 2 times delta naught plus 2 times the pairing energy requiring. Now for D6, again, crystal field stabilization energy. Let's do first the high spin case. the high spin case corresponds to 1, 2, 3, 4, 5, 6. So this would be equal to 4 times minus 2 over 5 delta naught plus 2 times 3 over 5 delta naught plus the pairing energy for this pair of electrons. So on the high spin configuration, we get minus 8 plus 2. Sorry, minus 8 plus 6 is going to give us minus 2/5 of delta naught plus P. And for the low spin case, now the configuration would correspond to 1, 2, 3, 4, 5, and 6. So we're going to get 6 times minus 2 over 5 delta naught plus 3 times the pairing energy. So this is going to be equal to minus 12 over 5 delta naught plus 3 times P. Now let's go for the last 3 cases. D7, for the D7 configuration, we're going to get 1, 2, 3, 4, 5, 6, and 7 on the high spin case. So the crystal field stabilization energy for high spin would be equal to 5 times minus 2 over 5 delta naught plus 2 times 3 over 5 delta naught plus 2 times the pairing energy, which would give us minus 4/5 of delta naught plus 2p. Now the crystal field stabilization energy on the low spin case would correspond to having this configuration. In the low spin case, let me erase this high spin labeling, we're going to get 6 times minus 2 over 5 delta naught plus 3 over 5 delta naught times 1 plus 3 times the pairing energy. So minus 12 plus 3 gives us minus 9/5 of delta naught plus 3 times the pairing energy. And for D8, luckily for us, D8 is going to have only one case. So 1, 2, 3, 4, 5, 6, 7, and 8. So the crystal field stabilization energy for D8 would be equal to 6 times minus 2 over 5 delta naught, the energy of the lower orbitals, plus 2 times 3 over 5 delta naught, plus 3 times the pairing energy, which is going to be equal to minus 6/5 of delta naught, plus 3 times P. And for D9, again, we're going to have a single configuration. The crystal field stabilization energy would be now equal to 6 times minus 2 over 5 delta naught plus 3 times 3 over 5 delta naught plus 4 times the pairing energy. We're going to have 4 paired electrons. So minus 12 plus 9 is going to give us minus 3 over 5 delta naught plus 4 times the pairing energy. And with that, we are done with all of the possible cases. Thank you very much and have a good one.